If you're still here, you're a trooper. We are back with the 16 steps that make up the horizontal procedure. I got everything set up for horizontal and started reading through the book, got all the settings done up, and started to realize that horizontal here for the first 13 steps is exclusively conducted with a time mark generator, something I do not have. And looking at eBay, I find that the time mark generator cost about $200, and I'm not going to buy a $200 piece of test equipment to calibrate this oscilloscope. It's just not going to happen. If there was like a little kit to build one, I may be down with that, but yeah, not going to do that. So I get to step 12 and I get to step 13, and it's finally that I get to step 14 that I do not require a time mark generator, and this is the first step that doesn't need it. So we're going to start here at step 14. Here's step 14. Take a signal 50 millivolts and set it up for 5 divisions on 10 millivolt setting, right? Switch it over to XY mode, and you should see 5 millivolts or 5 divisions of deflection on the screen. If not, adjust R760. Let's do that now. Oh, I've got it set up. I got 5 divisions right here on an arbitrary signal of 100 kilohertz. That's why I back down the intensity for the camera and roll it over to the end of a division here. And I could see that it is not 5. I'm going to have to make a slight adjustment here to bring this into specification. And 60 is the X gain. It's shown right down here by this expansion card, by the power supply. So there it is. I'll adjust it, and then I have to go and reposition to see if it's correct. Now it's set up. 5 graticules. Perfect. This step is done. In the next one, we're going to check phasing. We've already set up our channel 1 in the previous step. 10 millivolts XY, and now we're setting up channel 2. Sine wave generator sits at 150 kilohertz, so we'll set that up as well. And they want us to make an observation based on this information, so we're going to do that now. What they want us to observe is an opening in the center of this as we line it up for 0.4 or less. Now it's hard to see really the center graticule with all of the marks in the way, so I just move it over a little bit, and I'm looking at it as compared to one over here next to it, and I'm saying that no, it's probably good. It's probably on 0.4 opening in the middle, so I'm not really seeing a problem. I'm not seeing a terrible issue, so I'm gonna say that this is okay. From here, move channel 2 to ground, which gives us a straight line. So set the generator up for 50 kilohertz, a 5 division line. And I've done so here and centered it on the scope. Just to ramp up the frequency all the way to 2.5 megahertz, all the while seeing that at 2.5 megahertz we maintain at least 3.5 divisions. So let's do that. 2.5 megahertz. I'm looking at the scope now, and now I'm just going to adjust for reading, and I see 4.24, 4.6, right? And display should be at least 3.5. So it looks like it passes this test. We can move on to the next test. The next step uses an external oscilloscope to test this oscilloscope. This is the first occurrence of this. And it wants the Tektronix set up in this manner right here. And then we take our external oscilloscope and connect to R707. Here's my connection to R707 on the timing board. Having set the VAR hold-off knob all the way to norm, it wants to check that the resulting value is greater than 3 milliseconds. Actually, it says greater than 3 milliseconds, but less than 7 milliseconds. Good enough for me. Set it up on the Handtech, and I see that the delta is 3.7 milliseconds, which shows it to be in an acceptable range. Right here. I'm supposed to rotate that knob all the way to max and check that the hold-off has increased by a factor of 10 or more. Turn that to max. Resulting delta is now 60.5 milliseconds. It's definitely increased by a factor of 10 or more. On that, I'm going to say that the test was a success. And that concludes horizontal, though I'll say we really didn't do much because I don't have the required test equipment to do the first 13 tests. The new section, I've set up all the initial control settings to match the required procedures for trigger. Trigger will be 9 steps. So the next step is going to use the multimeter to do this test and calibration. And we already have the trigger source set for channel 2. And we have all the traces set up to align exactly to the middle. Everything is shunted to ground. And what we're going to do is we're going to take a reading right off of pin 1 on the sweep board on channel 2. or having the trigger set for channel 2. And then we're going to record it. And then we're going to do it again for channel 1. And then we're going to adjust the offset so that they match. So here I am at pin 1 taking the measurement, and I'm going to record that value down. We're seeing about 22.8. So I'll write that down. That's for triggering on channel 2. I've adjusted the trigger source for channel 1, and I'm going to take that reading again. And I see 37.3, an obvious discrepancy, for which I'll have to make an adjustment. It also states that these values should be less than 100 millivolts, but it doesn't tell you what to do if they're over 100 millivolts. So these are under 100, so I'm not worrying about it. Trying to make this adjustment is way down here by the switch. We can see the screwdriver pointing towards it. Now for channel 2, we're seeing about neg 22, neg 23. For channel 1, we're seeing about neg 22. The thing is really squirrely, so getting it that close seems about as good as I'm going to get it. I went back one more time and got it within a millivolt. I decided to go and clean the wipers, which made it easier to work with. So yeah, I got it even better. Now I'm definitely closing out this step. In step 2, we have to set up a 50 kilohertz 2.2 division signal on the display. And when it's on the display, we're supposed to be able to rotate the trigger level slowly while adjusting the trigger sensitivity so that the trigger is just at the threshold of being able to be maintained. This one is under the main circuit board, but is positioned sideways so it can be reached. By under the circuit board, I mean all the way down here. It is the one all the way on the right. And here is the waveform set up on the display. So I'll just be adjusting this knob right here while I make the adjustment on the side. I'll point out that before the procedure begins, you have to turn the volts per division to 1 volt per division. This was actually one of the more difficult ones to accomplish, probably because you're dealing with 2 knobs at the same time. And I was able to get it all set up. I'm going to turn down the intensity here to just be able to trigger on a certain portion, and I have it right there, and it just barely triggers in one particular position. You see the trigger light, and if I adjust that pot anymore, then it won't trigger at all. You can see it's just barely triggering, and I think that is what they're looking for, is the minimum trigger sensitivity there. They don't talk about it, so that's the best I could do. So I feel as though I've accomplished this, so I'm going to move on to the next one. I'll point out that the wording says so that the trigger is just able to be maintained, which is basically what it's doing. Now we're setting up for step 3, auto trigger centering with a 50 kilohertz 5 division display set up as shown in the book. I have that display now set up on the oscilloscope. It says to set the volts per division to 0.5. I have done so. This time we'll be adjusting the front pot, which is positive number 434. All the way to positive. My assumption is, as you back off from the optimal position, you lose trigger. And you're supposed to bring this into the center of the point where it starts to work, which is right about here. So I'm going to lock it down right there. That seems to be the center of the positive triggering, which I've set up from positioning left to right as center graticule. So I'm going to call that good. I'm going to do the opposite. We're going to put the slope in, like that, and then we're going to turn this way, and then we're going to adjust the other pot basically in the same manner, and that's going to be the middle one. Again, this is the same routine. It's all about finding center, where it comes in the sync, which graticule it is, which graticule it falls off again and comes back, and then centering it between those 2 graticules. So we're going to call step 3 completed. Step 4 is adjust B trigger sensitivity. So we're going to be working with channel 1, setting it for 10 millivolts, and the source for A is going to be external. And we're going to do this again with 2 probes using the same signal, one going into channel 1, the other one going into the external input. And the generator is going to produce a 50 kilohertz signal such that the voltage will produce 2.2 divisions on the display. Look on the display, we see that this signal is set up just fine. Source is set to external. There's our external input. That's to set the A trigger level for a steady display. See that we already have that. Set the horizontal mode switch then to B. The horizontal mode switch is set to B. And adjust the B trigger level for a stable display. We can see if I rotate the B back and forth in the middle, you can see that stable display. I'll set one up and there it is. All right, so the B is now set to a stable display. We set the channel 1 volts per division to 0.1 volts, which you have right here. And then we're doing the same thing with B that we did with A. which is to make an adjustment on the sensitivity that it is just able to trigger. And if you look at it, I already have it set up to a point where it's just able to trigger, so I don't need to adjust this setting, but I will point out where it is. 627 won't be found on the diagram because it's way up here on this circuit board, which is strange that they wouldn't mention that, but whatever. This is where the location is of the B trigger sensitivity. So now in step 5, we're checking the internal A and B triggering. We're setting up here for a 10 megahertz signal with 3.5 divisions on the display in channel 1. I have that signal set up and inputted it to channel 1 on the oscilloscope. Supposed to turn channel 1 to 50 millivolts on volts per division. End up with a very small signal here. The goal is now to get this signal to stabilize, to trigger under a set of conditions as set forth in table 6.8, which I will show now. This is table 6.8, and we're going to work on normal and out first. I'm on normal and slope out, and I was able to trigger on that signal. Very sensitive, but I was able to trigger on it. I pushed the in, and we can see in, it worked just fine, inverted slope. So those two worked. I'll move over to the next setting, which is PP Auto. This is Auto. I'm going to now adjust this. You see in both extremes of this knob, I'm able to get it to come in, so that's good. We'll switch to slope out, and we can see again it worked fine. It says set the horizontal mode to switch B. I want to check to be done with the B trigger. There's a thing here that says B runs after delay, and apparently it's very easy to trigger upon that. I'll show you right here. So I turn right there and it triggers on that, but they wanted to trigger on somewhere else besides that, right? So basically what I'm doing is I'm taking it off of that, we lose the trigger, and then I want to come to something where I could trigger on somewhere else besides that, and there it is. So I'm out of that area, and I could still trigger, which is what the book is asking for. This entire process will now be repeated with channel 2. I'm not going to do it on video. In the next step, there's a slight setup change, and the generator gets set to 60 megahertz with a 1 division display on the oscilloscope, and the process is repeated all over again. The field tech doesn't do 60 megahertz. I have set up the RF generator to do this, and the hand tech is monitoring the frequency to make sure it's stabilizing right now slowly. And what I've got is a 1 division 60 megahertz frequency on here. Note that the knob had to be pulled out for 10 times magnification at these frequencies. But yeah, the setup was possible due to the Heath kit. I was able to complete all of these tasks again at 60 megahertz as prescribed in the book here in section P. So I'm moving on. Q calls for another minor adjustment, followed by cranking up the frequency to 100 megahertz with a 1.5 division. To set this up for 100 and check it on the hand tech, but I had to disconnect the hand tech because it was robbing ever so little of the amount that I needed to get 1.5 for the display. The oscilloscope was able to pass all of the tests at 100 megahertz. That section 5 is now concluded. This next step has to do with high frequency and low frequency reject triggering. And the first one is high frequency reject. And what they want is a 1 kilohertz 6 division display as viewed from the trigger view button, which I will show. Once that's set up, they want you to increase the frequency of the function generator until 4.2 divisions are displayed, and see that that frequency falls within 30 to 50 kilohertz. So let's take a look. Here's the actual signal that I have coming in. If I look at the trigger view, I could see that I have 6 divisions, and that's what I'm looking for. So now I'm going to hold in the trigger view and increase the frequency until we get down to about 4.2. It's hard to say because I can't readjust for, so I got 1, 2, 3. It's about right there. I'd have to count them. That's 1, 2, 3, 4, 5, 1, 2. That's 4.2 right there. And it is showing 31 kilohertz. inside 30 to 50, so we're going to call that good. Now we're going to set the switch to low frequency rejection. This time we're going to start at 500 and we're going to decrease until we hit 4.2 and see where we end up at. 80, 70, 60, 50. I'll go back to a finer scale. There's 4.2. We're looking at 38 kilohertz, and that sits between 30 and 50, so that is good. This test is complete. I have to take exception with step 7. The settings do not leave you in a perfect position to get a test like this going. Forget about the challenges of the fact that I need to use my RF generator because the field tech won't work for this given the frequency. But not only do they reference the wrong settings for this, they also reference the wrong table. They mentioned table 5.8. There is no 5.8 in this book. It only goes up to 5.5. They're talking about table 6.8, which already shows that this is riddled with errors. This will be proved to be a challenge to do, and I'm really not going to lose any sleep if I don't get through this specific step. I was in fact able to set this up doing 35 millivolts, 10 megahertz, using the trigger view shown here. The stability of this wave was able to be attained using these settings here in table 6.8. So that portion was able to be done. The next step is to set up the RF generator for 60 megahertz for 120 millivolt signal. The problem is with this RF generator at 60 megahertz, the best I could do is about 6 millivolts, and that's about it. So it doesn't look like I'm going to be able to do that step. Looking further down, we see 100 megahertz at 150 millivolts. That's not going to be practical either. It looks like this is pretty much the end of what I'm able to do for the testing of this step. So step 8 has a setup that wants me to put a waveform into here for 6.4 divisions to be displayed. Goes into channel 1 as well as the external input, which I will display on the oscilloscope. Then what it wants to do is rotate the A trigger level in a way that, as displayed here, that when the slope is in, that it would trigger along the entire positive slope of the waveform, and when it's out, trigger along the negative part of the waveform, and that the trigger should not be displayed when it's on the extremes, regardless of where the button is. I didn't find this entirely intuitive. I got the slope out right now. It is set up, and as I turn it, we can see where there it stopped triggering on the positive, and there it stopped triggering on the negative, and that's where it came back. And that's positive and negative. Now if I put the slope in, I'll go to positive. That's positive right there. And negative right there. And the fact that it shuts off from both its extremes has already been shown to be the case. That's about it. I got really nothing else to say about that. And since there's no adjustment, I'll move on to the next step. Last test, I set it for internal, and then I set the trigger level to maintain a steady level, which it is. I set this for ground right here, and then I hit the signal sweep reset button as shown, and now the screen is blank, right? And then the ready light should be illuminated, which it is, right? Now it says set the channel for DC, the light goes out, which it does, right? Check that the light goes out to signal sweep. Now press the button several times and see if the light illuminates every time I hit it. And you can see, if only for a brief second, it's illuminating. And that's all that they want you to do. So I'm saying this step works. We're done. And this is the final battle. This is the external Z axis. And this is 2 steps to end the calibration. We're setting up a 5 volt 50 kilohertz signal in step 1. We're splitting it off. One side is going to the Z axis in the back. The other one's going to channel 1. And we are viewing this sine wave, and we should see that the bottom portion of the sine wave is notably brighter than the top portion. In looking at the sine wave, we could see that the output is correct. So we move on to the next step. The next one has a whole step for adjusting the amplitude calibrator. It almost seems like this could be better served by plugging the hand tech into the amplitude calibrator and adjusting it with a hand tech. You can clearly see this makes a lot more sense. It's running about 550, 560 millivolts. We have to knock that down a bit. You know what, on the very last step, this cal jack, I couldn't find that resistor. I've looked all over for it. R984 in all the documentation. I can't find it, and quite frankly, I really don't care. I'm not concerned. I'm going to let this one go. So this is it. This concludes calibration of the 2235 AN USM-488. So if you had one of these oscilloscopes and you were concerned about attempting the calibration, you see that a lot of this can be brought into the ballpark with general bench type equipment, especially if you don't have a terrible field tech and you have a real function generator, right? The hand tech does well to assist in a lot of this. So now I have my analog oscilloscope back on the bench ready for service. Thanks for watching.